So now we're going to go, before we were just in the affine case and just two-dimensional cones with some astonishing structures attached to them. Now we're going to go to actually we're going to go to the smooth case. So we're going to take, from the point of view of this stuff, we're taking the least interesting ones because we're taking the smooth ones, and we're going to actually work with complete toric surfaces. And in fact, it turns out a smooth, complete toric surface is actually projective. So you can actually, so we actually are dealing with smooth projective toric surfaces. We'll talk about the Riemann-Roch theorem, Noether's theorem. We'll talk about Earhart polynomials, and we'll give an interesting application when we deal with reflexive polygons. And so the place to start is to understand the universe of these things. So let's classify smooth, complete, toric surfaces. You don't need the smooth. But it turns out that in dimension 2, complete things are projective. I continue to be mean to batteries.
Yeah.
That's right. I'm using it to charge my cell phone. So like I say, in dimension 2, if you're complete and toric, you're automatically projective. And so the setup for our fan is that, we have I'll call it U0, U1. Then we go around. We'll have UI, UI minus 1, UI plus 1. And then the final one. So the idea is we really have R rays. So we have R rays. And we have R smooth cones. So that's the idea, that's our smooth, complete toric variety. And on the toric variety, what you get then, so each of these rays, it's a wall, so it gives a curve. And so, and since they cycle around, things cycle around, so you get, right here, you get, and then here you get CI, CI minus 1, CI plus 1, and so, and then dot, dot, dot. So you get this nice cycle of curves, and then the question is, if I want to do, and so this is on X sigma, this is sigma. If I want to do intersection theory, well, it turns out all these are transverse intersections. So when I take two successive curves, the intersection product is 1. And then it's the same game we played earlier. That when I have these guys, that's a wall. You look at the top dimensional cones that lie on each side, and there's the stuff on the other side. So here we're basically doing stuff, from chapter 6, doing the wall relation stuff, and you really do get that UI minus 1 plus UI plus 1. And again, because of the smooth stuff, it's just going to be some integer multiple of this. But now BI is just an integer. So we no longer have the restriction. So it might be positive, it might be negative, it might be 0, it might be -1. And so all we know is this is a smooth toric surface, and so I can say that's just going to be some integer. And then the point is that when I take CI intersect itself, it's going to be minus BI. And remember, minus BI comes from when you write the wall relation in the standard form. So that minus BI is that. And so we have that. And then, of course, you always have permission to subdivide further. Because if I just take one of my cones, say UI plus 1, what's the obvious way to subdivide that? What ray should I add? Yeah, just the sum. And that's a plus there. And so I subdivide it into two new cones. And when I do that, what have I done in this picture? Because there's UI and UI plus 1. So notice that my original cone right here is this one. And the fact that it lies in the two walls means it's the intersection of these two guys. And somebody just said blow up, and what you do is you just blow up. In fact, notice I can label each one of these with the self, with the self intersection. And here's minus BI minus 1 minus BI. And when I do that, I'll get proper transforms. So I'll put tilde because it's proper transforms. So this is now, when I've blown things up, and I get this new exceptional curve. And the point is that's a -1 curve, because notice that the B there is 1, and so that B gives a minus, and so here I have a -1 curve. And so the point is in terms of just classifying all possible, there's an infinite number. And but what's interesting is that the way I get these infinitely many ones, well, it looks like basically I'm going to just get more and more -1 curves. And so what you want to classify are minimal. Surfaces, which means that I have no -1 curves. And so the theorem is that up to isomorphism, all smooth, complete toric surfaces come from a nice infinite list. The nice infinite list, they come from basically a P2, P1 cross P1. Can somebody guess what the other ones might be? And it's the Hertzebruch surfaces. And it turns out that H1 is not complete because it actually has a -1 curve. So it's those that they come from this via blow-ups. And of course, notice that this is a blow-up at a torus fixed point. So what I have right here, that's actually a fixed point of the torus action. So I'm always blowing up at torus fixed points. And this is really, and it's really successive blow-ups. Now, it turns out this theorem has a couple of nice consequences. The one that's going to be relevant for us is that in this setup where I have these UIs and these BIs, what's interesting is that this system clearly has to be constrained. I can't just put sort of the rays anywhere I want because of the constraint that everything has to be smooth. And so if I keep putting smooth things here, you have to make sure when I close it up, it remains smooth. So there's clearly got to be some sort of constraint. And what's happening is what's being generated is by these BIs. So it's got to be a constraint on the BIs. And the constraint is that when you add up the BIs, remember there's R of them because there's R rays, then you just get 3 times the number of rays minus 12. And the proof really has 2 steps. One is that you verify for the basic surfaces. And basically these either have 3 or 4 rays, and so this is a completely harmless calculation. And then what would be the next step? So suppose I know it for these basic guys. Then what would you want to prove? Yeah, you do induction on the number of blowups. And so the idea is you show that it remains true after a blowup. So you assume it's true for a bunch of blowups. So you essentially assume it's true in this case. Then you do a blowup, add one more cone. So you've added, the corresponding BI is just 1, and so you just have to check how each side changes, and you'll discover it's pretty harmless. Okay, so now let's do some Riemann-Roch stuff. And I'm going to talk about curves and surfaces. And so for curves, let's suppose that C is a smooth, irreducible curve. So now I'm not necessarily in the toric situation. And you take D as a divisor on the curve. And then Riemann-Roch really has 2 parts to it. So I think there's an algebraic part. And the purely algebraic part is that, given D, you get this nice sheaf. And then, of course, we know sheaf cohomology, and so you can take the Euler characteristic of the sheaf you get from D. And so this uses chapter 9. So the question is, what is the Euler characteristic of this sheaf? And notice that in this case, because it's a curve, this is simply the dimension of H0 of C, OC of D, minus the dimension of H1 of C, OC of D. And so it really is just this little sum. And then what it says is that it's going to be the degree of D, because remember in this case, on a curve, divided just a bunch of points with multiplicities, just add up the multiplicities, and then you get the degree of just the structure sheaf. Oh, sorry, the Euler characteristic of the structure sheaf. And then so that's the algebraic version of Riemann-Roch. And now, historically what happened is Riemann basically didn't know about that. And so he sort of did an inequality. Then Rock came along. He didn't know what chief cohomology was, but he basically brought the canonical divisor, because when you zap this with Serre duality, you can turn it back into an H0, and that really led to the more classic formulation involving D and K minus D. But then you get the more intrinsic one when you use Serre duality to turn that into H1. And so that's sort of the modern formulation. But then there's also a topological aspect. So you're working over the complex numbers, because the question is, what is the Euler characteristic of the structure sheet? So this is this very, very algebraic looking object. It's this sheaf cohomology and all this stuff. It's basically, it's H naught of C of O minus the dimension of H1 of C of O. So that's very algebro-geometric. And of course, the whole point is that it's 1 minus the genus. And the genus is, and so this is the topological genus, which I can think of, is basically, I just take the rank. For example, if you're thinking in terms of cohomology, you just take, the integral cohomology of the curve, and it turns out that, this is basically a free abelian group of rank 2G, where G is the number of holes in the Riemann surface. But it turns out another way to think about it is, notice that 1 minus G, I can think of this as 1/2 1 minus 2G plus 1. So, that plus that is 2, with that gives 1, and that, of course, gives that. And what's interesting about this is 1/2 times the Euler characteristic, because you see these are the Betti numbers, so this is just the alternating sum of the Betti numbers of that curve. So again, this is a really topological invariant that is equal to this thing from algebraic geometry. So that's Riemann Roch in dimension 1. Now in dimension 2, let's see, let's do it here. So this is surfaces. Now let's suppose that X is a smooth, irreducible, projective surface. And so we have D as a divisor on X, and then we also have the canonical divisor. And just to remind you about some of the stuff we're doing, is notice that here we're doing some chapter 9 stuff, here we're doing some stuff from chapter 8. So we really are using the tools that we have. In fact, that's one interesting thing. Some people have asked us, why is surfaces are such a nice topic? Why did you wait till chapter 10? And the answer is, to really do full justice to surfaces, you need stuff. And so you need the sheaf cohomology, you need the canonical class, so you need all that machinery you built up in the earlier chapters. And so then Riemann Roch has a similar kind of thing. There's an algebraic one, which says that the Euler characteristic of the line bundle you get from the divisor, so you want to compute that. Now notice that now it's an alternating sum of 3 things, because it has an H0 minus an H1 plus an H2. So there's now 3 terms that you have. But it turns out that it's 1/2 D dot itself minus D dot K. So this is something that you sort of compute out of D, just like, here we had this one that you compute out of D. And then there's sort of a error term, and the error term is just the Euler characteristic of the structure sheet, just like here. So there's a nice similarity there. That's nice. But then, of course, there's a topological part. which tells you how to compute this in terms of the topology. And it's not purely topological. You'll see that there's, it's got a mix in this case. In fact, in this case, the topological part has a separate name. It's called Noether's theorem. And that's Max Noether. And so what it is it's the canonical class dotted with itself, plus, and this again is the Euler characteristic of the surface. So again, this is, and x is now four-dimensional. So this is basically E of x is h0 minus h1 plus h2 minus h3 plus h4, because as when we're over the complex numbers, x is two-dimensional, but that means it's four-dimensional as a real manifold, and so the integer the usual singular homology goes up to dimension 4. And so anyway, it's that divided by 12. And one small hint of coming attractions is that 12 is that 12. So 12 is a good number. So one thing I'm going to do is I'm going to actually prove part of this in the toric case. I'm going to prove Noether's theorem for smooth toric surfaces. For smooth, complete toric surface. And what I'm going to do, well, what does Noether's theorem have? Well, it has three quantities. It has that one, and that one, and I will compute each one separately and show they satisfy that identity. And so, of course, the first one is this. So I'll just call x my smooth toric surface. And so remember, this is going to be dimension of h0 of O of x minus the dimension of h1 of O of x plus the dimension of h2 of O of x. Now I claim we know what those guys are. And why 0? What theorem says that? It's a vanishing theorem. And what's the first vanishing theorem that Hal proved yesterday? Remember, that was the de Mazur one. And what do you need for de Mazur's vanishing theorem? You need an F divisor. Well, it turns out that the 0 divisor is Nef. Because you zap the 0 divisor with a curve, it's greater than or equal to 0. And so, but then these are the global functions. And how many global functions are there on a complete variety? And so in fact, what is this guy equal to? Not just 1. So we're doing pretty good. Now, k dot k. Well, remember, we actually know what the canonical class is. And again, this is something we learned in chapter 8. This is minus the sum of the CIs. That's an R. So remember, that's the picture we had here. These are the torus invariant divisors because they're on a surface. And so just minus the sum of them is the canonical divisor. And of course, when I take k intersect itself, the minus goes away. So I basically just get all possible intersections. But of course, a lot of the intersections are, when the curves are disjoint, the intersection is 0. when the curves meet, it's 1. And so the case that's interesting is when you have this. And in fact, what you get is because one of the things you get is when I equals j, and that's ci dot ci, and that's minus bi. So when I equals j, it's that, and when I is not equal to j, roughly speaking, every curve meets 2 others, so every curve is going to contribute 2. I've got r curves, so I get 2r. And so that's basically what this is. But now notice this little formula that we have from the classification of smooth toric, smooth complete toric varieties. We know what the sum of the bi's is, and so that's going to be 2r minus 3r minus 12. And so in fact, that's going to be, when you work it out, that's going to be 12 minus r. And so k dot k could be negative. That's actually okay. Now the final thing we need, so remember we're trying to assemble this. So I've got that. We need this one. Now this is a pretty fact, because you'll notice that we've been mentioning various chapters, and one chapter we haven't mentioned is chapter 12. That's where we actually talk about the topology of toric varieties. So let's suppose that X sigma is complete of dimension n. Well, from a topological point of view, what you have is, this thing, it's a bunch of, it's a union of orbit closures. And orbit closures look like, basically C star to the ends. And so what that does is it gives you a pretty nice cell decomposition. And so when you you realize the fact that you have this stuff, it fits together pretty nicely. And then it turns out that, so you have the Euler characteristic, which in this case, again, that's dimension n over the complex numbers, so it's 2n dimensional over the real numbers. So you're, trying to compute this guy. It's the rank. Oh, sorry. I'm doing integer cohomology, so I'll do rank. Turns out that one of the really nice formulas that you prove in complete generality is that it's simply the number of n-dimensional cones. And so this is Theorem 12.3.9. Now, it turns out we saw an example of that in Hal's lecture yesterday, because he took P2 and he computed the Hodge diamond of it. Now, these are the HPQs, but when you understand how the Hodge decomposition works, sort of the rows give you the cohomology. And so the rows give you H0, H1, H2, H3, H4. And so when I do this alternating sum, I have a 1 here, a 1 here, and a 1 here. And that's in the even degrees. So in fact, the Euler characteristic of P2 is 3. And there are three two-dimensional cones. And the point is that, and this is actually not the technology you use to prove it. You do a quite different proof in chapter 12. But anyway, it's simply the number of that. So we actually know what that is. So I'm keeping that on the board there. And so what we get in this case is in dimension 2, so what we get is that we get our E of x, because remember x is our smooth toric surface. So E of x, well, it comes from this fan. It comes from the number of two-dimensional cones. So it all comes from counting these guys. But now comes a nice fact that's special in dimension 2, because I have two-dimensional cones, I have one-dimensional cones. How do those numbers relate? And the answer is they're equal. Because, when I go around, I basically get R rays, I'll get R cones. So that's special to dimension 2. And of course, what's the notation we use for the number of rays? That's our number R. So R is we've been using for the number of rays. And so what that implies is that when I look at k dot k plus E of x over 12, when we computed k dot k over here using the classification of smooth toric surfaces, and notice we got 12 minus R. That's looking good. Then I add in this guy, which is R, and I get 1, and that's the Euler characteristic of the structure C. So that's the proof of Noether's theorem for smooth toric surfaces. This is obviously not a formula that generalizes to higher dimensions. It used a lot of special stuff that's going on. So, to try to do this in general definitely takes different techniques. Okay, so that's Riemann, Roch, and Noether's theorem. Now I want to talk about sort of Earhart polynomials of lattice polygons. So Hal introduced the basic ideas yesterday, and what I want to do is sort of think it through in the basically in the surface case, and then realize that I can also think it through using the Riemann-Roch theorem. So we're going to get sort of a dual perspective on what's going on. And so here's a lattice polygon. And remember that these guys were introduced in chapter 2. Then the Earhart polynomial so that's EHR. Hal used L. I'm going to use K. And what you do is, remember, you take your lattice polygon, you expand it by K. You intersect with M. And again, here I'm thinking of K as a positive integer, and I just count that, and the point is that so here I get this Earhart function. The theorem is that there's actually a polynomial that does it, and in the two-dimensional case, turns out it's always the degree of the Earhart polynomial is always the dimension, and so this is R2, and so it's basically going to be a little quadratic, and so it has there's something times k squared, something times k, and a constant term. Turns out the constant term is 1. Turns out that the coefficient of k squared is just the area of P. And here I'm just doing the usual Euclidean area. And then what you get here is you get 1/2. And what you do is you look at the boundary of P and look at the lattice points on the boundary. And this result is sometimes called Pick's theorem. For if you take k equals 1, you just get the area plus 1/2 times the lattice points, plus 1. And so that's a very pretty formula for things in the plane. Now I want to view this using Riemann rock. Now there's one slight awkwardness, because of course when I get P, I get x sub P. So this will be, a toric surface. This will be a nice ample divisor. But the problem is I can't apply Riemann rock to this because this might be singular. So we have to think a little bit about what's really going on if I'm going to actually try to apply Riemann rock to this. So what I do is I'm going to take a smooth refinement. Now if you think about it, that's actually, so what happens now is that I have a picture that sort of looks like this. But I'm going to erase it because it's actually not so nice. So we have, here's sigma p, a bunch of cones. But the problem is these might be singular cones. But of course, if you think about it, back in the first part, we learned how to resolve those, so I can actually get a smooth refinement. So this has a smooth refinement. And I'll call that sigma. And again, that's created using this technology. And so we get a map from x sigma to xp. Now let's think about what's going on. So let's again just remember the structures we've been learning about. So we have d sub p, which is ample. And d sub p has a support function, phi. And there's various subscripts I could decorate with. I'll just call it phi. And then what happens is I can pull back and it turned out the pullback, the way that it works, is I basically use the exact same support function, phi. But so I had phi was linear in each of these cones. So in particular, it's also linear in all these cones. And now, of course, this guy had some Cartier data. And if you want to think about in terms of Cartier data, there was an m sigma that worked here. Well, I just use the same m sigma in both of these. But now the fact that I'm using the same m sigma here, so here I have strict convexity with respect to this guy. What about here? What do I have? Just convexity. And so in particular, what I get here is that, so this will be base point free. So this is ample, this is base point free. So that's the setup that I have there. And so what I'm going to do is I'm going to apply Riemann rock for this divisor on this smooth. And again, this is a smooth projective toric surface. So this is where I can apply Riemann rock. And the question is, what does it give us? Well, I should say one other thing is that one of the games that happens is, of course, when you have a divisor on a toric variety, you get a polytope, P sub d. Now I can build the polytope using the support function. but these guys have the same support function. So in fact, when I take this, when I build the polytope of this, what do I get? I just get the original P. So that's the interesting thing, is that I've got something here. Like I say, I've taken my, because like I say, I get this toric variety that's possibly singular. I get this one that's smooth. I take the canonical, the divisor we get, from the facet presentation of P. I get a slightly funkier thing here, but it still remembers what polygon it came from. So that's going to be pretty important. So now let's compute the Earhart polynomial. So, because guys say here's the definition of the Earhart polynomial that looks pretty simple. Well, let's compute it in a slightly more sophisticated way. So here's, and I should decorate this, with the, so this is the Earhart polynomial of our lattice polygon. So I should put in that. So, this of K is the number of lattice points. But now if you remember your description of global sections, if I take global sections of this sheaf, well, basically it's the polygon of D. This just scales it up by K. And so, and it's the lattice points of that. And so when I take the dimension, that just counts the number of lattice points. And again, the polygon I get is just my P. So I can interpret this like so. But now comes something really interesting. Because remember that KD is Nef. Because of course, besides global sections, I have all the cohomology, which we package into the Euler characteristic, because this uses, the H naught, but it uses all the higher cohomology. But what happens to all that higher cohomology? Vanishes. Why? That's the de Maizière vanishing theorem. And so this is actually, we tried to say vanishing theorems are cool things. This is an example of why vanishing theorems are cool. They turn this into something. It's quite powerful. So this is the de Maizière vanishing theorem. So this again is chapter 9. But what does de Maizière vanishing say? Well, it's going to be, well, again, now we use Riemann rock. And remember, it's the divisor dot itself plus the divisor dot the canonical class. Oh, I wrote it the other way. So it's that divided by 2 plus the Euler characteristic of just the structure sheet. But remember, we already computed this guy. And what did we get there? 1. And so let's write this out. So that's going to be 1/2 d dot d times k squared plus 1/2 d dot k times k plus 1. And of course, the reason I'm writing it this way is to compare it to the Earhart polynomial. And so when we put these two together, we get a wonderful result that, so like I say, we did this thing that looked, slightly strange. We resolve, we pull back. And notice that I'm not necessarily taking the minimal resolution. I'm taking any resolution. So I give myself permission to do a lot of really dumb things. So there's infinitely many choices for here. Ideally, we'd want to take the most efficient one because we know what it is, but I could use any. But what happens in this case is that comparing coefficients, what we get is that you get this geometric interpretation of a d dot itself. And then also, let's see, so let's see, you were supposed to yell at me because what's that supposed to be? It's supposed to be a minus sign. But that's still a plus sign. And so what we get is that minus d dot k is the number of lattice points on the boundary. And again, here this is really just Z2 because we're doing a very concrete situation. And this is proposition 10.5.6. So to finish off, I want to do a particular example. Yeah? Oh, yes. Yes. And let's see, did I mess that up here? Oh, here I did it correctly. Thank you. Yeah, so that's boundary. So sort of the complement of the other. So let me do a particular case that's going to be, that basically, so now let's use all this machinery to compute what 3 plus 9 is. So here's a fun example. So I take just E1, E1, and minus E1, minus E2. That's usually E2. So I just take this little perfectly good lattice polygon. Of course, it's not a random one because this is actually reflexive. And then the dual, because notice that the dual does, we are going to be playing some games with the dual here. And let's see. So how do I get? So here's P, and this is in MR, which of course is the plane, and then its dual is in NR. And so how do I get the the normal family? I just take normal vectors. Like one normal vector comes out here, so I get a ray coming out that way. A normal vector right here, that's basically minus 1, 2. So it goes up at a funky angle, and then this one does, and this one is basically 2 minus 1. So there's the dual fan. And so this is sigma p. And it turns out that xp is singular, as we expect. But it turns out that because we're reflexive, and so I need to come up with a resolution of singularities. But because we're in the reflexive world for polygons, that's like really easy to do, because here I just drew the normal rays. If I actually draw the normal vectors, because that's minus 1, 1. This is minus 1, 2. And this is a 2 minus 1. Actually get a very nice triangle there. And of course, what's the toric variety of this guy? So if that were my lattice polygon, what toric variety would I get? That would just be P2. And so, and this is the usual thing that, if you have a mirror pair, sometimes one gives you a smooth toric variety, sometimes one gives you something singular. But notice that what's nice is that, and this is something that we work through, especially in some of the problems, is that, to get the normal fan, you do it by coning over the facets. That's pretty good. But now, notice that I'm just, I'm lattice distance 1. I'm lattice distance 1, I'm lattice distance 1. Doesn't give me much room to work. So now let me just take the lattice points on the boundary. So I'm taking the lattice points on the boundary. And what's really interesting is that notice that when I take the lattice points on the boundary, I get a little triangle, and it's what we call an empty simplex. It has no interior lattice points. And in dimension 2, an empty simplex is smooth. And so this game right here, and the reason it's empty is because this is lattice distance 1, so there's basically no room for anybody in the middle. So the fact that this guy's reflexive and this guy's reflexive basically says that when I take, because normally I'm not really sure how to get my resolution of singularities. You have to go compute, continued fractions and stuff like that. But here, because we're in the reflexive world, I just use the lattice points on the boundary. And so in fact, when I use those guys, so like right here, so this single cone, and so that's a cone in the normal fan, I now using these two lattice points, I get 3 smooth cones. And again, that's smooth because this being an empty two-dimensional simplex forces that to be an integer basis. And so there's my, and so what I get is that, and so basically I resolve, see, what do I want to call this? So I get sigma uses boundary lattice points of P dual to get a smooth refinement sigma of sigma p. So now you see I'm back in the game that I was playing, because remember, I had a lattice polygon, I got a smooth refinement. So I played this game, and in this case I didn't really know a huge amount about it. In this case I know a lot about it, because I know exactly where it comes from. It basically uses the dual intersect M. Or actually, but it's not intersect M, of course, it's intersect N. This is always one of the challenges when you're dealing with a reflexive pair. This guy lives in M, this guy lives in N. And so it's that. So now so this is the last page. So like I say, I want to compute I want to compute 3 plus 9 using Noether's theorem, which again is sort of the topological part of Riemann rock. Because notice that I use the algebraic part to make this stuff going on. So now I'm going to use the other part. And so what do we know? And we've already worked this out, is that so Noether's theorem is this guy. And we already know, again, that's, the vanishing of chapter 9. And again, just a reminder, K is K of X sigma. That's what we learned about in chapter 8. And so we get that that's 12. So let's now think about what's going on. So I want to compute some interesting things. Because if you think about it, we have various ways to compute k dot k. I want to give you a totally different way of computing it. Because again, that's the richness of the world we're in right now. So how do you compute k dot k? Well, the answer is to remember that this is a reflexive polytope. So again, our goal is to compute this guy. And this is, remember, on my refinement, because that's where I apply Riemann rock. So remember, the whole point is that D sub p was anti-canonical. And again, remember, that's because when I look at the facet presentation, it's always all the A sub rows are 1. And so when I take the corresponding divisor, I get that. And so again, because remember, so the idea is that the anti-canonical divisor is ample. So we got that. And so then that says that the support function is 1 on every minimal generator. Because remember that the support function lives here, and it's equal to 1 there, it's equal to 1 there, it's equal to 1 there, and it's linear on cones. And the point is that D on X sigma has the same support function and notice that it's equal to 1 here, it's equal to 1 here, it's going to equal to 1 on this line, so it's equal to 1 here and here. So in fact, what we get is that so basically the construction of X sigma says that phi equals 1 on every minimal generator of X sigma. But what that tells me is that what I'm going to get out of this is, again, the canonical class. And of course, there's a sign floating around. So in fact, I get minus the canonical class here. And so what's interesting is that, see, what I have is I have this map right here. And remember that, and so what I'm doing, because, basically, dp pulls back to d, but dp is basically the canonical divisor. And what we showed is that the pullback of the canonical divisor is the canonical divisor. Now that's rare. And in fact, This is what's called a crepant morphism. And you look up crepant in the dictionary, like, what is that? And the answer is it comes from the word discrepancy. A discrepancy is there's a gap between them. And so to say that there's no discrepancy means that it's crepant. And if you happen to know Miles Reed, who created the term, you realize he has a sense of humor that just really likes terms like this. And so there's certain parts of birational geometry where crepant morphisms are very important. And here we're actually seeing an example of one in this mirror symmetry context. But then what do we get? We get that k dot k. So now we're going to use what we learned about the Earhart polynomial. So what's k dot k? Because remember, that's what we're trying to compute. Well, k is this, and so that's minus d dot k. And that's what we proved using the algebraic version of Riemann rock, is that minus d dot k is just the number of boundary points on the lattice. But this is like a pretty so in one sense, this is complete overkill to compute k dot k to get 3 this way, but it sort of shows how some of the ideas fit together. So I've done that. And then the other final part, so I am taking my obligatory 5 minutes.
Sorry.
And so anyway, so so we now finally have, because that was 3 and that was 9, we have 3 plus 9 is 12. And I have one final comment, and then I'll turn us loose for lunch. The final comment is something that's a little more systematic going on, because that's obviously cute, but definitely on the silly side. What's more serious is what the 3 is so here we had P is reflexive polygon. And P lives in the M, so that's the lattice points there. So this was the 3. And then the 9 was this. So it was the boundary points on the dual relative to the lattice in M. So we have these two reflexive this reflexive pair, and the point is, for any reflexive polygon, those add up to 12. So that's, and there's some very fun papers that sort of go into this, and one way to prove it is the Riemann-Roch theorem. And so what I did here in this special case, you can actually do for any reflexive polygon. So that's a good place to stop. So let's go have lunch.